This video on First Updates Now is made possible by viewers like you and also the following sponsors. SOLIDWORKS is free for first teams. Over 80% of US engineering schools and 370,000 plus companies use SOLIDWORKS to design great products. SOLIDWORKS can help you design a great robot on desktop or on the cloud. Go to solidworks.com/first to register your team. FRC Premiere Night is back on Saturday, February 25th. Submit a unique video showcasing your team's charged up robot progress by Thursday, February 23rd at firstupdatesnow/premiere23. Premiere Night is a great way to engage with the community. Get more information and submit your video at firstupdatesnow.com/premiere23. And we welcome on to the Open Alliance Show, team number 1757. Wolverines coming out of New England district as well too. So guys, we're happy to have you on and coming out of Massachusetts. Why don't you introduce yourselves? Let us know what you do on the team, and we got a lot to talk about today.
All right. I'm Landon. I'm the fabrication and CAD lead.
I'm Charlie. I'm the team captain.
I'm Luke. I'm the programming lead.
I'm Steve. I'm the drive coach and one of the senior mentors.
So for 1757 today, you're going to hear more about arm joints, a test bench, alpha intake, CAD, arm control programming, a whole lot of stuff to go through here today, guys. So I'm very excited to hear more about what you have. Why don't you start us off with what do you want to dive right into with your team and your robot?
All right. So first off, going like big picture, we decided to go with a 3 degree of freedom serial arm joint. So what that means is we got, 1 link, 2 link, 3 link, and we actually call them shoulder, wrist, and elbow. And looking at that, the big consideration is the joints between each of the parts. So we actually have a 3D printed demonstration of our joint. So we made this out of just 3D printed material, and mostly to prove the point of we can rotate things nice and freely, and also so that way we have that center access hole, because this year we're planning on routing cables to the links up and up and up by running actually through the cables. So this is just one of our prototypes, but this has been working actually pretty well. We have multiple sets of bearings in here. You can actually see the needle roller bearings on the inside there. And we have a couple of thrust bearings. So this, we actually just last weekend decided not to use exactly this design. We're going into a different design, which you can actually see the roller bearings on the inside and some of the thrust bearings and some of these. Moving down to the shoulder joint, like the elbow joint's the more important joint, because that's where a lot of stuff ends up happening. But the shoulder joint is pretty similar structure. When it comes to fabrication and construction, this is actually like 3 separate parts of sorts. So if we have the link that goes out, we have these 2 side parts that also come out, and we also have this block in the center, which a circular part is going to attach to onto carbon fiber rods, just for rigidity's sake, which we actually have in the back over there. So moving down to the shoulder joint, this year we're planning on using chain drive for everything. So a big part of that is you need a lot of torque, and to be able to drive that up from where we want at the base all the way up, chain drive is our main go-to. I don't think I have some, but so this is actually like the CAD of the older idea if we were to fabricate it in full. You can see there is, sprockets on the side, and we're actually planning on using the max spline tube in the middle in order to transfer from the wrist joints at the bottom all the way up. So there's going to be essentially 2 sides to this. As you can see, there's 2 sprockets. The elbow joint is actually going to have 3, because one is going to drive the elbow joint, and one is going to drive the wrist joint through this middle spline upwards, and we're using the inside of the spline in order to, as I said, route cables. Yep. Going a little bit more onto the arm, we're thinking about our states and where we need to put these stops, because another part of this arm is that the holding spot, you can't like run through itself. We're not doing offset joints. So because they are one after another, our hard stops are actually very important. And another thing that we use for this is we find it very important for the wrist, especially our hard stop, because a large decision that we made this year is actually to not use pneumatics at all. So originally we were debating using pneumatics in order to lock our arm position, but after doing some calculations at our worst case scenarios, the amount of current pull required by the motor in order to hold that position, we considered to be low enough that we didn't need pneumatics. So wrapping back to our end stops, having a starting configuration that holds itself in place purely by end stops is a very important part. As you can see, this diagram here shows what we plan on having our starting configuration like. Another part is we saw that our wrist joint for our ground intake, we could actually, if we moved out from the elbow to this wrist joint here, we could keep this this end stop actually also for the ground intake, which has been a bit of a deciding factor. So we were experimenting a little bit beforehand because nothing ever starts at the beginning of just we go straight with this. And the real reason why we're deciding to use a 3 degree of freedom arm is the flexibility that it gives with regards to picking up items. Like this is just some sample that was done in order to show that we can, if we have the ability to like eject a cube or a cone outwards, we get a lot of ability to just do these like crouched in position all the way out, score, come back in.
You guys keep answering a lot of the questions I keep thinking of as we go through here because this is very well explained. The one thing that pops in my head, when you have those degrees of freedom, are you looking at from like the time to actually like go from being stowed in your robot to actually scoring on there? Does that change at all based on how many degrees of freedom you're looking at? Because you have to move more parts at once?
Not really. When it comes to programming, that since all of them are moving at once, it's essentially the same as if one of them was moving like individually. Since you adding more degrees of freedom, you end up getting a little bit more power of the motors because you get to expand outwards simultaneously. You don't have to wait for one motor to go to a position. You have 3 different parts.
Well, I know we got a lot of different parts of your robot to keep continuing on to. What do you want to talk about next?
All right. So we actually have a demonstration of just the shoulder joint part of our arm to prove for a programming perspective if we are able to do that. And it worked out pretty well. We learned a couple of lessons with regards to like feed forward controls on simple arm joints, but moving forward into more difficult arms, we're planning on having a little bit of a more rigorous approach with regards to control in order to make sure that we can maintain a position. I've been like slightly debating a bit of some center of gravity math with regards to the whole weight of the bot in order to figure out proper arm angles. And that's actually what we have attached. Want to, Steve? Well, it's not shown in the sign.
Yeah, here's our little prototype arm with our intake on it, which we'll get to in a minute. But it's just hooked up here. We have some chain on the side, driven by a Falcon right here, onto some gearing. I believe it's roughly 5-to-1, and then you'll get the gear. So obviously not super strong. That's nowhere near the amount of gearing we'll have on the actual shoulder. But yeah, rotates pretty well. Just up and down sort of thing.
Is that the counterweight that you have in that right now? Is that something that would stay on the robot, or are you looking at doing something different to have a type of counterweight for that?
No, there's not going to be a counterweight. It's going to be pure motor control to have a counter torque.
Gotcha. I was just curious. I'm like, wow, interesting flail you have there. But yes.
Yeah. So what kind of sensors do you have like on every single joint? How are you dealing with doing that?
So this is actually in the bad camera angle because we have an absolute encoder on the side. On the other side, that's actually going to be for a arm relative position per joint. So at the actual joint part itself is going to be where the absolute encoder lives because there's going to be backlash from the gearing and the drivetrain. So having the absolute encoder there is like a very crucial part.
And are you doing like for your jumping ahead a little bit, talking about your software? Are you going to be doing this from a like pre-programmed positions on every joint, or are you going to be running more a true like inverse kinematics, like controlling the end effector's location in space?
So we actually have a simulation of this currently. I'll try and make it a little bigger. So we're planning on using inverse kinematics fully. In a recent blog post, we did show a little bit of our inside math. See if I can remember the keybinds. So, oh, wrong button. So we're planning on controlling the end effector's position properly. I'm sharing on the screen right now.
Sure, we'll bring that up.
So a big thing is we're showing the end effector's position into set states. Take the page up past that. And so like intake state, going straight into our scoring state, coming back. So full inverse kinematics with trapezoidal profiling on the end effector position and rotation in order to have that smooth motion. So a big thing, as you can see, is that we're not like colliding with the geometry of the grid as we're going back. So having that smooth control instead of at our end effector position is very important in order to prevent collision and possibly break joints.
That's very cool. Yeah, I mean it's one of those things where, you know, every degree of freedom adds an order of magnitude of control difficulty. And so you know, having 3 degrees of freedom on this arm, you can do incredible things as long as your software is buttoned up tight. But it looks like you know, knowing that you guys are doing simulation, and it seems like you're way ahead on the control theory side of it, should be feeling pretty good right now.
Yeah. A big thing that we should actually note about our team is that we only meet in person on weekends as like a full team. So when it comes to stuff like CAD and programming, that's a bunch of like midweek tasks for us. And so grinding those out individually, fully remotely, is like a really important part in order for us to stay ahead of the game. So like all this stuff is all separated. So while the robot simulation code is all going, the arm control is all going, the intake simulation, all the CAD for that stuff's being done at the same time. So that way, when we're on weekends, we can actually use all of our time as effectively as possible.
Well, it definitely shows that you're putting in a lot of extra work to get this robot going.
You know, it blows me away to say that you're as a team only fully meeting on the weekends. How do you communicate otherwise, like during the week? I mean, I know you're not meeting necessarily, but are people working at home, I'm assuming, too? And how do you collaborate to where you're as successful as you are as a team?
A big part is communication. As a team, we use like Discord to go back and forth. So a bunch of our critical design decisions are actually decided virtually. So we use Discord to go back and forth. We actually have Tuesday, Wednesday, Thursday night calls. So right now we're actually skipping a night call for the sake of having the show.
Well, thank you.
Yes. So keeping together as a team, even if not in person, is a like very large part. So yeah.
I know you guys got a couple more things you want to talk about and show off as we start to wrap up. So tell us about what else you want to cover, and then anything next to come for Wolverines as we look forward.
Cool. All right. So moving on to the thing that's right in front of us here, we actually have a intake demonstration. So we saw the effectiveness of the EveryBot intake, and we said, why invent something better when it just works? And to prove the it just works point, like there's not really any difficulty with regards to picking up any pieces here. It could be at interesting angles. It can just like somewhat be there. Doesn't have to be perfect. So the for construction of this, it was practically taken off the EveryBot. The one major, or actually there's two major changes that we made from the EveryBot. The first one was instead of using 2-inch compliant wheels, we're actually using neoprene rollers on it because of the grippiness and the fact that it goes out. Especially at an end effector, we want to reduce weight, so having the least amount of stuff at the end is very important. Another big change is instead of, they had an interesting belting and gearing system, but one of the belts was actually on the inside of it. And from experience from last year, we were like very scared of putting belts in places that could get exposed. On our last year robot, the intake belt fell off like numerous times just because it was on the outside and it got hit on something like the hanger.
So that's why we have these double plates here to kind of protect the belt on the inside.
Well, guys, I know there's always so much to cover, and time always goes fast with this. Before we let you go, anything else you want to wrap up with, or anything else to look forward to when we see you in just 3 short weeks?
Yeah, so we were talking about all this arm stuff, but a big part is how do we control the arms? So we're planning on having all 3 of them at the bottom. So through by putting the chain and rolling the chain upwards, we actually are thinking about that. A big consideration we saw, and we actually looked at the 971 CAD, is to have a chain drive at the end to reduce the amount of force on any given gear. And we're also looking at putting versaplanetaries in the input stages, just so that way we can get the amount of gearing needed. And yeah, it's about summarizes it.
Greg, I don't know about you, but this has been incredibly impressive on the Wolverines so far. So, guys, kudos to you and your team so far. Really well explained, and I can't wait to see what your team brings. Make sure you keep following Wolverines and their build blogs on Cheat Delphi and also on the 08 Discord, and we'll see you back on here in 3 short weeks. Good luck, guys.
All right, see ya.
Good. Thank you.
This video on First Updates Now is made possible by viewers like you and also the following sponsors. SolidWorks is free for first teams. Over 80% of U.S. engineering schools and 370,000 plus companies use SolidWorks to design great products. SolidWorks can help you design a great robot on desktop or on the cloud. Go to solidworks.com/first to register your team. FRC Premiere Night is back on Saturday, February 25th. Submit a unique video showcasing your team's charged up robot progress by Thursday, February 23rd at firstupdatesnow/premiere23. Premiere Night is a great way to engage with the community. Get more information and submit your video at firstupdatesnow.com/premiere23. Don't forget to like, subscribe, and ring the bell to stay up to date on our new videos. Keep the conversation going and provide your input to our content. Watch our live shows at twitch.tv/firstupdatesnow. Join our Discord at discord.gg/firstupdatesnow and check out Fun FTC on Facebook, Instagram, and Twitter, and First Updates Now on Facebook, Instagram, TikTok, and Twitter.